For the Lewis relationship, we're going to have to look at convection and conductivity. For convection, we have the heat transfer, which is equal to the heat transfer coefficient times the temperature of the surface minus the temperature of the environment. And we also have the mass transfer, which is the mass transfer coefficient times the concentration of the surface minus the concentration of the environment. For conductivity or conduction, we have again a similar two equations. You have the heat transfer for this, which is slightly different. It's the negative conductivity times the change over temperature over the change in position. And for the mass part, you have the mass diffusivity, which is the diffusivity constant times the change in concentration over the change in position. Now, we're also going to need the Sherwood and the Nusselt number next. For the Sherwood, we have the mass transfer coefficient times the diameter over the mass diffusivity constant. And for the Nusselt number, we have the heat transfer coefficient times the diameter divided by the conductivity. And now these result in two equations that are very similar. You have A times the radial numbers to the B power to both. And then the last one, you have the Schmidt number for Sherwood to the C power and the Prandtl number for Nusselt to the C power. Okay, so the Lewis number, which will come into play a little bit later, is the thermal diffusivity over the mass diffusivity relating mass to heat. Now, for the relationship, we're going to need to get to a point where we can use that. So we have these two equations. And if you use, and if we look at the different part, the last one, we're going to have the Schmidt number, which is equal to the viscosity over the density times the mass diffusivity, and the Nusselt, not the Nusselt, the Prandtl number, which is the viscosity over the density times the thermal diffusivity. Now, with that, we can cancel out and we can do Prandtl over Schmidt, which after these two cancel out gives you the opposite of the Lewis number, which is the mass diffusivity over the thermal diffusivity. So if you come back and you look at our Sherwood and our Nusselt, which we originated with, and you do the same thing, putting the Nusselt on top of the Sherwood, you end up with the heat coefficient, heat transfer coefficient times the diameter times the conductivity times the mass diffusivity coefficient or constant over the, that's supposed to be Kc, which is mass transfer coefficient, so I have to over the mass transfer coefficient times the diameter. The diameter is canceling out, giving you the heat transfer coefficient times the mass diffusivity constant over the conductivity times the mass transfer coefficient. Now, because we know these two have similar parts at the beginning, we're only left with the difference of the Schmidt and the Prandtl, which we already looked at. And so we know that this is just equal to the Prandtl over the Schmidt number raised to the C power. Now, if we come back over here, we have the Prandtl over Schmidt being the mass diffusivity coefficient over the thermal diffusivity, which is the opposite of Lewis. So that tells us we have 1 over the Lewis number to the power of C, which is our Lewis relationship, which can be used in wet bulb problems, which we'll do next, and that shows the connection between mass and thermal transfers.